proofs with complex numbers just to show you how you might go about doing it. So this asks us to prove that the conjugate, that line over the top of z, so the conjugate of z is just z. Now, I'm working with complex numbers. A lot of times z will represent a complex number. So the way I start this is I want to prove this for all values. So I can't just pick a complex number like 1 plus 2i and show that it's true for that number. I have to show that it's true for any complex number. So instead, I say, well, let's let z be a plus bi. Okay, that's generic. It has a real part and an imaginary part, but a and b could be any number. So this, if I can prove it works for this, then it will work for any complex number z. Now let's put that into what we're trying to prove. So we're supposed to prove that the conjugate of the conjugate, so we take a plus bi and do the conjugate and the conjugate again, we're supposed to prove that that is equal to z itself. Okay, so notice I have exactly what they had here. I just replaced my z's with an a plus bi. I still have the same lines, everything. We need to work, there's nothing really to do on this side. On this side we need to work from the inside out and see if this actually works out. If they're asking us to prove it, it should. But here we go. Now remember the line over the top, that means the conjugate of the number, and that means we change the number in front of our imaginary part. So instead of a plus bi, that would be a minus bi. Now I've taken care of that first conjugate here, but I still have this one that was up above. And I'm trying to prove that that's equal to a plus bi. Okay, this hasn't changed at all. Well, we have to do the conjugate again to take that off. That means we change our negative to a positive. So I get a plus bi equals, you guessed it, a plus bi. Okay, and I've proven, I showed the two sides are equivalent with some generic complex number. Okay, this one will be a little more involved. I'm asked to show that the conjugate of z1 times z2 is equal to the conjugate of z1 times the conjugate of z2. So this is multiplying them and then doing the conjugate. This is doing the conjugate of each one and then multiplying. The little 1 and 2 don't mean we're multiplying by 1 and multiplying by 2 or squaring. It means we just have two different complex numbers, and they want to make sure we know that. Okay, so we start by saying, well, let's let z1, I'm going to put a line through my z's so you can tell they're a z and not a 2. Let's let it, again, be a plus bi. Has a real part and an imaginary part, and a and b can be any number, so that'll work for our proof. z2, we have to use different letters. Okay, we can't use a and b again, so let's maybe use c and d. So let's let it be c plus di. Again, it has a real and an imaginary part. C and d can be any number, so that will prove it. If we can prove it with a plus bi and c plus di, then it's proven for all complex numbers. Okay, so let's fill this in. So on this side, we're multiplying them first and then taking the conjugate. So we would have the conjugate of a plus bi, our first number, times c plus di, our second number. So again, that means we're multiplying and then doing the conjugate. On this side, we're doing the conjugate of each one. So it would be a plus bi conjugate times, I'm going to put parentheses around that, the conjugate of c plus di. And we want to show that when we do that, we get the same thing on each side. So we're going to do both sides. This one we need to multiply first. So I'm going to multiply here, FOIL. A times c gives me ac, and a times di gives me ADI. Now the bi times c gives me BC. I always put the i's on the end because they're not a number. Well, they are, but they're your I. And here b times b gives me BDI squared. I times I is I squared. Now let's organize this a little bit and simplify. Okay, so I'm going to do the full left-hand side, then I'll do the full right-hand side and hope that they end up being the same, and if not, check for errors. So here we go. Here I have i's and i's. Here is an I squared. Now remember, we can't have I squared in any simplified answer. Instead, we know that I squared is equal to -1. So if I replace this with a -1, that means I have BD times -1, which is, let me write down my other parts, positive BD times -1 gives me a negative BD. Well, the next thing I need to do, write this in simplified form, is gather my real and imaginary parts. The real parts would be anything without an I, so that would be my AC and my negative BD. The imaginary parts would be anything with a I in it, so that would be my ADI and my BCI. Now remember, I'm going to be taking the conjugate of this eventually. Well, to take the conjugate of it, I need to have it in the form real part plus imaginary part times I. And notice this is separated a little. So I put my real part together. I'm just grouping it off, okay? Plus AD plus BCI. Notice all I've done here is factored out an I, okay? And notice this is in the form of a complex number. I have a real part plus an imaginary part. So that when I go to do the conjugate, now I can actually do the conjugate, which is to change the sign in front of my imaginary portion. So instead of plus, I would have a minus there. So on this side, when I get it simplified, I have AC minus BD, quantity, minus AD plus BC, quantity, times I. Whew! Now, let's work on the right-hand side and see if we end up with the same thing in the end. So on this right-hand side, let's expand it. Well, first, we're supposed to do the conjugate of each one. So A plus BI would become A minus BI. And C plus DI would become C minus DI. Now we FOIL. We don't have what we have down here, right? We need to do some work. Let's FOIL. A times C gives me AC. A times a negative DI gives me negative ADI. Negative BI times C gives me negative BCI. And negative BI times negative DI, negative B times negative D would be positive BDI squared, because I times I is I squared. Replace the I squared with a -1, because we can't have I squared in our simplified answer. We replace it with its equivalent, -1. So now I have AC minus ADI minus BCI, and then BD times a -1 would be a negative BD. Again, let's separate my sides so you can see. Okay, we need to gather the real parts together and the imaginary parts together. So AC minus BD, those were the two without any I's in them. And then we had a negative ADI minus a BCI. Okay. Now notice here my real parts are AC minus BD, which is exactly what I had on this side for my real part. Okay. For these, AD and BC, notice they're both negative, so I'm going to pull out a negative, which would make them AD, positive AD, and positive BC, and pull out an I over here. So I have exactly the same thing on both sides, AC minus BD minus AD plus BCI, and over here, same thing. Okay, so it took a few tricks as far as arranging reals together, imaginaries together, factoring, for example here, the negative out that was in both terms, and factoring the I to the end. Okay, but we were able to prove that if you multiply two complex numbers and take the conjugate, it's the same as taking their conjugates and then multiplying them. You get the same thing.